Hi guys, BuildZoid here, and today I want to talk about CPU power, a bit about CPU power consumption and boost algorithms. So here's our CPU. It's an 8-core, and we have a power limit. So I'm just going to use abbreviations because I write really slowly. Power limit of say 80 watts, right? Which I did for convenience because 80 divided by 8 is 10, so we get 10 watts per core. We're going to have a temperature curve. Well, you're going to have a temperature limit and also a temp curve. So temp limit, let's say, I don't know, 100 degrees Celsius, okay? I'm doing that wrong, aren't I? Somebody's going to complain. Anyway, so you're going to have a temperature limit, right? So this is like CPU cannot exceed this temperature because that'll harm its lifespan. Power limit, this is just kind of a restriction, well, kind of an arbitrary restriction, honestly. Power limit is one of those things you just set for fun, really, because you don't really, like, there's a voltage limit above which the chip will die. There's a current limit, but like, if you push too much current through the chip, you're going to get too much electromigration. That's going to kill the chip. If you push too much voltage, you're potentially, well, you're going to, like, too much voltage translates into too much current, too much electromigration, dead chip. Or too much voltage translates into gate breakdown, dead chip. So you kind of have different mechanisms for how voltage will kill the chip. High temperatures also increase electromigration. So yeah, you don't really so much, like, you don't so much have a voltage limit as much as you'd have like a volt, like if you're going really smart, volt vs temp curve, right? So we have a voltage temperature curve, and then we're going to have a volt plus temp vs frequency curve. Now the temperature part of that is optional. You don't necessarily need it. It's just like, depending on how smart your boost algorithm, how smart do you want your boost algorithm to be? Well, at lower temperatures, you can hit higher clocks at the same voltage. So you'd ideally want to combine voltage and temperature into part of that, into that curve as well. So that's going to be another curve, right? And so basically what that means is you're going to have something that looks like, and we're just going to say that's optional. So we're going to do like a voltage, just volt frequency. Actually, no, because, wait. Trying to think how that'll look. Whatever, it'll be fine. Volt frequency, and that'll look probably something like that. Okay, and at some point you're going to need way too much voltage to get another increase in frequency, so it's pointless. You're going to have a voltage versus temperature curve, which is going to look probably, right, so if we put temp up here, that's going to look something like this. It'll be a curve, but I'll just use a straight line because I'm lazy. Right, so up here we're going to have, like, I don't know, 100 degrees Celsius, and voltage, at that point the chip shuts down. Well, actually, the funny thing about chips is that there's, like, a minimum voltage you need for the chip to run, so it would actually look something like this. Because past that point, like, it won't run anymore, so you can't turn it on anymore. So, again, you'd have just volts on that. And, you know, and this could be like our 100 degrees Celsius. Yeah, so that would be our temperature limit. And so we have all these lovely curves, right? And, you know, under an all-core workload, we're going to be hitting the power limit. We're not going to be hitting any of the other limits here. We're just going to assume, we have a good enough heatsink to stay under the temperature limit, so we're just going to bounce right off the power limit. And if we do that, let's say our chip does, so that's going to be 10 watts per core, right, / core, and that's going to be pushing, say, 4 gigahertz, right, at, say, 1 volt. Now, so that's going to be our 8-core load, but what if we were running a 1-core load? How far could we push it? Well, we're not going to be hitting the power limit anytime soon, right? We're running 1 core. We're literally running, if we don't change our frequency or voltage, we're going to still be doing like 10 watts, except it's going to be in 1 core. So ideally, right, in a perfect world, we'd want to be able to shove the entire TDP of the CPU into just 1 core. Now, physics is not going to allow that, because you'd need way too much voltage to actually get that much power consumption from 1 core, and your chip won't scale that far, and basically you're going to blow up the chip before you hit the like, you would never be able to hit the TDP unless you have like a 2-core CPU, because it's relatively easy to double your power consumption. It's very, very hard to like more than, well, triple it is also still possible, but past triple, like once you get past the point of like tripling your power consumption, it runs into the issues of like your voltage is probably so high the chip's going to die in a couple days. So yeah, that's kind of what you run into. But let's say, so we go one core, right? And let's say we can run one core loads at like 5 gigahertz and 1.5 volts. What kind of power consumption will that give us? Well, assuming temperatures don't change, because we're going to end up with something that looks like this. So P2 is our power consumption, new power consumption figure. And F2 is our new frequency. F1 is our old frequency. And we're going to multiply that by voltage, new voltage divided by old voltage squared. And then we're going to multiply that by old power consumption. Now, there should also be a temperature component in this whole thing, but the temperature component is really, really hard to model because it basically looks something like, well, actually, we need a graph that looks like we could have it go sub-zero because the temperature curve, like, it looks something like that. And this is like coefficient, not actual like power consumption. If it was actual power consumption, it would look something, I guess, like the. Well, actually, like it also changes, like the temperature coefficient also, like the component, well, not coefficient, component changes based on operating voltage because basically temperature tweaks your leakage and your leakage is related to your voltage. So you lower the temperature, it gets weird. So we're just going to ignore that there's a temperature component to this, and we're just going to say the temperature for all operating conditions is always the same, which in reality is not going to be the case because we have much different thermal densities after we solve this. So let's go through this, right? So frequency is going to be 5 divided by 4. Voltage is going to be 1.5 divided by 1, which is why I chose 1. So that's going to be nice and easy. So we're just going to have 1.5 squared right there. Or actually, we can still put 1.5 divided by 1, right? That's going to get squared. And then we're going to multiply it by our old power consumption per core. So we're going to go 10 watts right there. So that's going to be 1.25 times 2.25 and times 10. And the answer to that is roughly 28.1 watts. Okay. So now we're going to be doing 28. Let's just round it down to 28 watts per core. All right. If we go any higher on the voltage, that chip's probably going to die. We're just going to assume that this is the upper limit of our voltage. So here what we're going to hit is basically we're going to max out our voltage frequency curve, right? We're going to hit this point and we're going to sit on that and we're going to be, maybe in this area of the voltage temperature curve. We're going to hit like there and we're going to max out our frequency curve. So, we end up with this lovely configuration right here. Now, what if our chip didn't scale very well with frequency? Well, let's say our chip scales like, only 10% in frequency, right, for the same increase in voltage. So let's say 4.4 G and like 1.5 volts again. The issue is this is still going to pull, like the thing is, if we literally didn't tweak the frequency at all, right, if we just went 4 over 4, this was 1, you'd still end up with 22.5 watts of power consumption. Basically a lot. Now, if we replace if we run it with 4.4 instead of 5, we'd end up with 1.2, we'd end up with times 1.1. So we'd end up somewhere around like 23, 24 watts of power consumption. Still a lot, right? Like still very, very high because instead of having 10 watts going off in each core, you're going to have 24 watts going off of 1. So that's going to translate basically into very high single core temperatures because you have a very high voltage and that kind of thing. So yeah, this is kind of boost algorithm behavior if you try to get your algorithm to just absolutely max out the chip at any given moment. Theoretically, 2 core loads, you could still run this configuration, except you'd probably start hitting a temperature restriction at that point. So you might, like, if you go, so 1C, basically we have we basically volt limit, right? We run out of voltage. Now, if we go to 2 core workloads, we could almost run this again, but we're probably going to end up running slightly higher temperature. So our voltage, so like 1C, we could go here, right? That would be like 1 core right there. Now, if we hit 2C, we're probably going to, hit 2 cores. You're going to end up maybe like here. So 2 cores is going to have slightly lower voltage, so we're going to have to come down the frequency curve a bit, and we're going to end up at, say, 1.43 gigahertz at like 1.4 volts, right? Still very hot, because 1.4 volts is like 1.96, 1.4 times 1.4 is going to be 1.96, yeah, we're still going to have like a, almost 1.1 increase in power consumption, so you're going to be pushing about 20 watts per core. Still probably pretty damn hot. At this point, we also have a total CPU power consumption of 40 watts, which is mainly the reason why the temperature would actually kind of, like that's what basically lowers our voltage restriction, because if we were running any higher voltage, we'd actually be, at almost more than like half of the TDP of the CPU. And depending on your cooling system, 40 watts is nothing, but we're going to assume that we have like an 80 watt heatsink. Okay, so 40 watts is actually, at this point, starts being significant. 28 watts, not really. 40 kind of is. So that's that. Now, if we go up to like a 4-core load, if we could max out the TDP and run 20 watts per core, but we'd really quickly just slam into the temperature limit, so we're going to end up at like maybe here for the 4C. So that's going to be like 4 cores. Right, that's going to end up our 4-core workload. So we're going to drop all the way down to like here in frequency, right? So we're going to have a massive drop in actual voltage. So let's say, I don't know, we're going to end up at like 1.2 volts, and maybe like 4.1 gigahertz, right? We lose a lot of frequency going back to the 8-core settings. So at 4C, we lose a lot of clock speed. We lose a lot of everything, basically, because our temperature is so high. But we're going to hit maybe, I don't know, what's it going to be? Like, this is like, not like, we're just going to ignore that there's a change in the clock speed. And the voltage increase, it's going to be 1.44. So we're going to be running like 15-ish watts per core. Right? Or it could maybe even be 4.2 gigahertz. I don't really care. It doesn't really matter. But we'd be running maybe 15 watts per core, 4 cores loaded. That's going to be 60 watts, load. And actually, maybe your heatsink is a bit better, and so it'll slide a bit back up, right? And you might get a little bit more frequency. But basically, you see the idea, right? So basically, because your per core power consumption just kind of behaves like this is going to have a very high temperature. This is still going to have a pretty damn high temperature, because that is, a lot of heat in a small area. This is going to be a higher temperature just because it's a higher total power consumption, right? Like our total power consumption for each of these is like, this one's literally pulling, this one's going to be like, I don't know, 24 watts total. This one's going to be like 40 watts total. So actually this one would, well, no, it depends on which 2 cores are loaded up, right? Because if you have core 1 and 2 getting running this, then they're going to be hot. But if it's like core 1 and 8 that are running this configuration right here, then the temperature is actually going to be quite a bit better. So it also depends on like the layout of the die. But this is, not an insignificant amount of heat right here. When we go up to 4 cores, 15 watts, that starts hitting about 60 watts power consumption. We're still not bouncing off the power limit. Once we hit 6 cores, we're going to be stuck at like, I don't know, what is it? Need to calculate whatever 80 divided by 6 is, right? So we're going to be barely above the all-core frequency. So we're actually, yeah, we should just put that to 4.2 there. That's going to be more reasonable. And here we'd be at like 4.1 and like 1.1 volts, right? Barely above the settings for 8 cores. And then 8-core load, we're going to drop all the way down to here. So because of that, you're potentially going to have very high temperatures on 1-core loads and even on 2-core loads, but 4-core loads are actually probably going to be some of the coolest running, just because your overall total power consumption is relatively low and you're not running, you're not running that much power into each individual core. So yeah, that's kind of why you get, like, why I think, like, because basically AMD's boost algorithm behaves kind of like this. And the thing is for single core workloads, which are very, very light, like moving the mouse, or especially moving the mouse, like that is the only workload I've found that consistently maxes out the boost algorithm completely, because it's just so damn light. And the algorithm basically goes, oh my God, there's stuff to do. And it's on like one core and it's not actually that difficult to do. And it just, it just goes for it, because it's not going to get hot. It's not going to hit the power limit. It's not going to hit any real restrictions that it has enabled, right? And so it's just going to go absolutely nuts and going to give you insane settings that lead to a very high temperature, but it's because the chip is like, well, I'm not at any risk of degradation, or at least that's the way it should be configured. So that's kind of that. That's basically how the boost algorithm behaves on Ryzen CPUs. Is just like it pretty much keeps adjusting it adjusts the frequency and the voltage according to basically, I'm not sure if they're lookup tables or if they're curves. They could be either. It doesn't really matter, right? Like if it's a curve, it just means it's defined by an equation. If it's a lookup table, it literally means AMD's programmed a bunch of different like frequency values where it's like for 1.x volts at X temperature, you can run X voltage, right? Whereas there is potentially a way that you could just calculate that instead. There's like you can, model both to work equally. I assume AMD's using a curve because the frequency seems to be like the frequency changes very like gradually depending on the workload. It's like you can run 8-core workloads where, it'll, depending on the 8-core workload, it'll run a couple megahertz higher or a couple megahertz lower. Like Cinebench runs a higher frequency than Prime 95. Different settings of Prime 95 run at different frequencies, different settings. Like everything basically, like almost any workload has its almost unique frequency voltage profile. But especially like single core, very light workloads, they're just going to go absolutely nuts because the boost algorithm goes like, hey, I have the CPU has instructions to execute, and the goal of the CPU is to just complete as all instructions as quickly as possible. And so it's just going to go and max out the boost algorithm because the boost algorithm's like, well, if we finish them as quickly as possible, that's great, right? We're keeping the user happy. The side effect of that is that you're going to have basically really high temperatures. Because the other thing is to keep in mind with especially Ryzen CPUs is they have a lot of temperature sensors built into the die, but when you're checking the CPU temperature, it'll only ever give you the temperature reading for the hottest core. So if you're smashing power into Core 1 because the boost algorithm is doing its thing, Core 1 is going to be reading like at 70 degrees or something, right? And that's pretty disconcerting when you're sitting basically like, watching a YouTube video or something, but the rest of the chip is well below 70, right? Like the other cores in the chip could easily be like, maybe this core would be at like 30, or actually like, okay, not 30. This one might be at like 40. And that one might be at like 40, and this one could be at like 30, 30, 30, 30, 30. Actually, Ryzen can straight up shut down cores. So like these two cores out here might be at room temperature, right? Or actually, they'd be at like the temperature of the motherboard. Because obviously there's heat sources just everywhere and heat spreads anywhere with lower temperatures. So, yeah. That's something to sort of keep in mind about the boost algorithm. And the funny thing is, if you actually... like the thing that I don't personally like about AMD's boost algorithm is that if you actually take an oscilloscope and monitor the behavior of the algorithm on, say, single core workloads, you're going to see something where basically if we have, time, clock, you're going to see something that looks like, especially for single core workloads, instead of holding like a nice steady clock speed, right? Like say this, it'll constantly go like, it'll basically do silly things that, or at least what I consider silly things, where it'll do something like that, right? And it'll just, and the thing that I don't like about this behavior, right, is the reason I don't like this is, say on a second gen CPU, that's 4.35 gigahertz. And that's 4.3. So if you start doing, say, BCLK overclocking, what you're going to run into is that this stupid little spike of frequency is actually going to crash the chip, even though your average, because if you actually took the average clock speed from like here to here, your effective clock speed is like 4.3 something, right? Like these little nubs of extra clock speed do nothing for performance over a long time scale. but they are really bad for stability, because if you start messing, like, it's not going to crash the chip at stock, but if you start overclocking with BCLK, this little nub of frequency is going to go from being 4.35 gigahertz to say 4.5, right? When your chip is only stable up to 4.45 on single core workloads. And that's what I really hate about it, is just like, so you're basically like, this restricts your maximum average frequency, which I think is like a silly design flaw of the algorithm. Like, I really wish AMD gave us access to whatever frequency voltage relationship settings they have on their CPUs, because personally, if I was messing with overclocking Ryzens, I would just cut that end off. That way you would more consistently, because the thing is, it's easier to stress test a frequency that's actually constant, whereas a frequency that, because the thing is, like, these spikes would last a couple milliseconds, like literally a couple milliseconds, just long enough to crash the CPU, but not long enough to actually make any difference in terms of performance, especially because it's only like 50 megahertz more frequency. Like, 50 megahertz barely makes a difference at the best of times. And it's like, and when it's 50 megahertz every 10 milliseconds for 2 milliseconds, it makes no difference. It's literally irrelevant to performance at that point. So yeah, I'm not really a fan of the thing is, this is really clever from like a sort of marketing perspective, because you can have a really high peak frequency that you hit for like a incredibly short period of time, where it's just like, yeah, look, our frequency goes that high, and it's just like, yeah, but it's not actually doing anything for that long, so it's useless. So it, like, if Intel had AMD's boost algorithm, Intel would be shipping 9900Ks with a 5.5 gigahertz boost. And I like, or like a 5.4 gigahertz boost, because basically the other thing that's kind of cool about the whole algorithm is that, because your max safe voltage changes based on operating temperature, at low loads, you can run really high voltage, because it's like, oh yeah, the temperature's so low, we can smash the voltage for days. The side effect of that is that at low loads, you also get really high core temperatures, because it's like per core temperatures, because you're smashing all of that power into a very small space. But yeah, it's just kind of like that. That's how the algorithm behaves. And actually, I can't wait to, like, I wanted to do a video basically showing an oscilloscope shot of the, because you can't actually get like a frequency proper frequency readout, but you can just monitor the voltage of a Ryzen CPU while it's running to see how with an oscilloscope, you can see the boost kicking on and off, because basically whenever, like, because if you actually went and graphed the voltage with it, you basically see the boost algorithm doing its thing, because you see the little voltage spikes around the frequency spikes, right? Because obviously, like, 4.35 is going to be at like say 1.45 volts, whereas 4.3 is going to be at like 1.4 volts, right? So if you actually monitor the output voltage of the VRM, you can see the boost spikes, because you can see that the voltage is 50 millivolts higher for no apparent reason. And the funny thing is, you can have like monitoring software running, and it won't really pick up on those same, couple millisecond frequency spikes. Also, I think those couple millisecond frequency spikes are bloody useless. But yeah, that's just the boost algorithm. So on second gen, it's actually like, I tested this and I was like, oh yeah, that's exactly why it's crashing, because it's just dumb. But I assume on third gen, this whole algorithm has basically, because it seems to me that the 7 nanometer process, like, it seems to have basically increased the voltage, like peak voltage that AMD can run. Because if I'm not mistaken, I remember reading that the new fit limit is like 1.47 volts for low workloads, right? So basically what I mean by that is like this point in this curve, well, more like this point, actually, I scribbled over it, but like that point in the curve, right, that's going to be 1.47 right there. And it's going to be at whatever the max boost frequency is of the CPU. So yeah, so the new the new voltage limit is 1.47 volts, but the clock speed doesn't really scale that far, so you end up with very high temperatures, because, if you're running all core on like especially in like a 65 watt TDP CPU, right? Like if we did this, but the CPU's TDP was 40 watts, then we actually get a really silly power disparity, right? Because our 8-core workload would be 5 watts, but our single core workload could still be 28, right? Like, we're still nowhere near, like, even with a 40-watt power limit, if we're running 5 watts per core for 8, like, you know, you have to run 5 watts per core for 8 cores. But single core, you can go all the way up to 28 because it's still not beating that 40-watt power limit. So basically, depending on how the process scales, you end up with what AMD's made, where it's just like, yeah, it behaves really silly. I assume Intel hasn't bothered to come up with something this elaborate for their for their boost system because they don't need it, right? Like, their chip, if it's like, you just kind of set like, hey, this for this power consumption, run like for this many cores, run this frequency, for this many cores, run this frequency, for this many cores, run that frequency, right? Whereas because AMD, I guess basically their process kind of like the chips can't clock that high, so AMD's solution to that is we have a boost algorithm that basically is ridiculously aggressive in terms of you know, just opportunistically going like, hey, we have just enough power limit and just enough temperature limit to boost the frequency by another 25 megahertz if we raise the voltage by another 50 millivolts, and it's going to do it, right? It's going to do it. It's like, I'm not violating any limits. Go for it. The side effect of that is potentially very high per like single core temperatures, and you know, at idle, that's going to make the whole chip light up. Basically, like, it's going to make it look like the whole chip lights up because Ryzen doesn't report average CPU temperature; it reports peak temperature. So, yeah. Hopefully this makes sense. Also, this right here is not like, I don't have this information from AMD. This is just information based off of like my own testing with my 2700X. I am getting a 3700X soon, so once I get the 3700X, I really hope to do the video with the, like, I'll do the video with the oscilloscope showing I first have to check that it behaves the same way as the 2700X. Actually, no, I did this at Gigabyte with one of the engineering sample chips, which behaved really weird because it was an engineering sample chip and those things are basically broken as far as I'm concerned. But yeah, we messed around with one of those, and it basically did what the 2700X did. So once I get my 3700X, we're totally doing a sort of Ryzen voltage, like operating voltage on an oscilloscope. The other thing to keep in mind is like your average voltage is gonna, like, the thing is, the algorithm will actually, if you graphed out a single core workload, right? So if you have different workloads, like say I wanted to wrap up the video, but I just thought of something that I wanted to point out. So if we have work, and then we have volts right here. I mean, volts. Oh no, idiot me, doing it wrong there. Work, volts, and time, right? Always time. So if you have a workload, so let's say that's 0 right there, 0 work. And then you have like 1 core workload for, right? So that's going to be 1 core workload for a very short period of time. And this is going to be like a 1 core workload for a long period of time. And then we're going to have, say, a all-core workload for a long period of time. If you actually look at the voltage on Ryzen at idle, true idle, it's going to look like that. As soon as it detects a very short workload, it's going to just go wham, right? Because it's very short, it's very light, it's not going to get hot, so the voltage goes way up. But then we get another like low load workload, and it's going to go way up, and then it's going to realize, wait a minute, we're still doing stuff. Okay, start stepping the, it's going to start stepping the voltage down a bit, and eventually it's going to settle around a voltage that it considers safe for that period of time, right? It's because basically, if you also graph the temperature, you would see something that like your temperature would basically go something like this, right? You'd have the temperature spike, and then the temperature would drop back down, and then here you'd have the temperature spike up, and it would keep rising, right? And the chip would be like, oh, wait a minute, we can't, like basically it would start lowering the frequency, lowering the voltage to get the temperature under control. And then when you hit an all-core workload, it'll actually also boost up initially quite a bit, and then it'll sort of settle down to a long-term safe voltage. So it also behaves kind of like this, which is why, you move the mouse, like this is like mouse moving, and the algorithm basically freaks out and gives you that. But you do something like 1 core Cinebench, And you get this, where initially it thinks, okay, this is a light workload, we can boost all the way up, and then it's like, wait a minute, this isn't finished yet. We need to slow a bit down, like for the safety of the chip. So yeah, hopefully I'm gonna try do a demonstration of this with when I get my 3700X. Because the chips do behave like that. And the funny thing is actually, like, I'm drawing this as a straight line, but actually you'd still have little peaks of voltage. Because for some reason, like, I think that's a behavior that AMD just needs to take out of their algorithm because it makes it really unpredictable and annoying, in my opinion. Like, because these little, boost nubs, they don't do anything. They don't increase your performance very much. But if you're messing with like BCLK overclocking or PBO or that kind of thing, they are actually annoying to deal with because they're a stability hazard. Whereas they aren't a performance booster because they don't happen frequently enough to make a difference to your performance, and they don't boost high enough to make a difference to your performance, right? Like, if you spend 10% of your time at 4.35 gigahertz and 90% of your time at 4.3, wouldn't it not just be better, right? Like, wouldn't it be better if your chip just spent 0% at 4.35 and 100% at 4.325, right? Because this is potentially stable. That potentially isn't, right? Or let's say 4.45 to make it look like we're overclocking, right? And so let's just whack 100 megahertz on top of everything. Like, this isn't stable. This is actually faster than this, because 4.45 gigahertz for 10% of the time, you can do the math on that, but basically it works out that this is going to be faster ever so actually, yeah, definitely going to work out, because in order to get an average frequency of 4.425 gigahertz, you'd have to be spending 50% of your time at 4.45, right? Which you aren't. So this is faster and more stable. So I really think like the little boost knobs, I think, are completely stupid, but they're probably some kind of like artifact of the way the algorithm behaves, and probably kind of like hard to eliminate. I guess maybe if they, like, one thing would be, like, personally I would really like it if you could just like set a hard limit on how far the like basically disable the top, like the peaks of the boost algorithm, because on multi-core workloads it's not a big deal. It's annoying when it happens like here. And it's just like, okay, could you get rid of that, please? That'd be great. Thanks. Anyway, so yeah, just kind of wanted to talk about this because I think it's an interesting topic. I will definitely try to do a demonstration of the like operating voltages of a 3700X when I get mine. And under a variety of workloads, from everything from like moving a mouse to one core Cinebench to like different number of threads in Prime 95, that kind of thing. So yeah, thanks for watching. Like, share, subscribe, leave any comments, questions, suggestions down in the comment section below. If you'd like to support, no, actually, whatever. If you'd like to support what I do here with actually hardcore overclocking, I have a Patreon. There's also Teespring. On Teespring, you can buy things like shirts, stickers, and posters, and hoodies, and that kind of thing. And if you don't want to buy anything, there's a Patreon where you can just support me directly, which also gives you access to the AHOC supporters Discord, where there's like some extra videos that I think are terrible, and I tend to hang around there. So yeah, if that's Patreon benefits for everyone. Don't have it tiered. So yeah, that's it for the video. Thanks for watching, and goodbye.